You'll recall way back when, or maybe you don't recall, but there was a moment when I said if a theorem has its own name, it's important. We haven't had a lot of them, but strangely enough, today we get two. Okay. Oh, they're easy. This is not a bad lesson. I think you'll find it pretty straightforward and easy. Two theorems that we're going to deal with today are, clicker that doesn't work correctly. Try that again. Rolle's theorem and the mean value theorem. Rolle's theorem named after a French guy named Michel Rolle. Mean value theorem, I don't know who did that. Nor do I care. I also don't know what order they went in. You'll understand why I pointed that out when we get further into the slideshow. Okay, so today we're going to talk about Rolle's theorem. We're going to talk about mean value theorem. You should be able to count to 10 in German. You just got 3. Anybody else? Sehr gut, meine Schatzi. Ja? Ja. Sprechen Sie Deutsch?
Nein.
Nein. Just mit den Numerals. Yeah. Okay, let's move on. Rolle's theorem. Okay? So, I'm going to start by, you know what, I'm not even going to show it to you. I'm just going to talk first. So let's try this. You're on level ground. You're going to start on level ground at the point A. You're going to end on level ground at the point B. And what are you going to do? You're going to take this big ball and you're going to roll it. You with me so far?
So far.
Okay. It's Rolle's theorem, and for Rolle's theorem, you're rolling a ball.
Whoa.
Right. Now, let me be clear. Michel Rolle, when he created this theorem, did not talk about rolling a ball anywhere. This is just something that I think will help you remember Rolle's theorem by rolling a ball. What are you going to roll? Where are you going to roll that ball? You're going to roll that ball up a hill.
But you said it was level. Oh.
Yeah, I put a hill on it.
Okay.
Deal with it. Okay. If I roll that ball up the hill, and then I roll the ball back down the hill, does it seem fairly obvious that at some point I have to hit the top of the hill?
Mm-hmm.
Is there anything difficult about that? That's what Rolle said. Now, did he talk about rolling a ball up a hill? No, I'll show you the calculus behind it. But he said, when you get to the top of the, or somewhere along the way, you've got to get to the top of the hill. Now, just to be clear, you could have multiple hills. He said it has to happen at least once. So we're going to keep it simple. We're going to have one hill. And on that hill, you're going to hit the top at some point in time. Let's call that point Q. What can you tell me about the point Q? Go.
It's the max.
Excellent. What else? Is that a local max or an absolute max?
Absolutely.
Both. So far in that picture, it's both. Good. All right, what else can you tell me about Q?
It's in the center.
Doesn't have to be. I just drew my
In
hill that
this
way.
scenario.
In this scenario, it appears to be in the center, yeah, but I could have made it a weird distorted hill where the top of the hill is way right or left. What else? Doesn't have to be. It appears to be in this picture, but doesn't have to be.
Yeah, it's like
Go backwards. No.
The ball has to pass through Q to get to B.
It does. Because it's a continuous hill. That's relevant. Good. What else?
When A is hitting Q from the left, it's going when it's going from the right to the left.
Ooh. Well done. Mathematically, it's increasing until you hit Q, and then it's decreasing. Excellent. What else? Oh, keep going.
Wouldn't the velocity also be slower than that because it has to go down?
I don't think we want to get into the velocity and acceleration stuff because this is just an example of Rolle's theorem. Rolle's, you know, he didn't have a ball in mind when he did this. He's just doing a function. Okay. What else? Limits. Keep going. What do you mean? Doesn't have to be. The hill could flatten out enough that you have a limit. Anything else? There's one major point you're missing, and that is, tell me about the tangent line at Q. It's horizontal. Yes. That's huge. Huge. Okay. So what's the relationship between the blue line and the ground? They're parallel. And if two lines are parallel, what do you know about them? They have the same slope. Good. So we're going to take all those puzzle pieces and put them together into Rolle's theorem. But again, I think this idea of rolling a ball up the hill will help you remember Rolle's theorem because you're rolling a ball up the hill. Could be a lot of little hills, but there's got to be at least one hill. Now, just to be fair, because we're going to start dealing with functions, it doesn't have to be a hill. It could be a valley. And you just change the idea. Instead of hitting the top of the hill, you hit the bottom of the valley. Same rules apply. Your tangent line is parallel to the ground. Both have a slope of 0. Good. Okay. So here's what Rolle said. In order to apply Rolle's theorem, there's a hypothesis. The hypothesis is the first part of the theorem that has to be followed. 3 parts. Number 1, the function has to be continuous. Okay, that's easy. Most of the time we're going to deal with a polynomial, which we know polynomials are continuous. Number 2, it has to be differentiable. You can take the derivative everywhere. That one's a little shaky, but we'll just pretend we know what that means. Number 3, you have to start and stop at the same level. So again, you go back to the picture. You start at A at level ground. You end at B at level ground. Okay, because notice, if I change that, if I get rid of that third part, and I start rolling the ball here at A, and I end at B, and they're not at the same level, that doesn't guarantee... Hello. Congratulations. That doesn't... Where's the other knucklehead?
He's in the back.
Okay.
Yeah, I know.
Way to throw him under the bus. It doesn't guarantee you're going to have a max. Okay, so again, those 3 things have to be satisfied. It's continuous and differentiable, and you start and stop at the same value. Then they introduce this idea of a C term, and a C term is what we call Q. It's the top of the hill, or the top of a lot of hills. Okay, depending on the function that we deal with, we could have a lot of different hills to calculate. Okay, how are we doing with concept? Are we good? Make sense? All right, good. Now, what does it look like? That's what it is in English, you know. Function goes from 1 y to equal y value, then slope tangent must equal 0 somewhere along the way. That point is called a C term. Okay, what does it look like when you apply it? Right, you take a simple polynomial. Okay, now, I kept it simple because it's the first time we're looking at this, but what can you tell me about that function?
It's quadratic. And differentiable. And
Continuous. It's continuous and differentiable. It's a quadratic, so what does it look like? Parabola. It's a parabola. Does it open up or down? It opens up, so will we have a max? Sorry, let me rephrase that. Will we have a hill or will we have a valley? We'll have a valley, okay. Now, from pre-calc, you could already tell me where that valley is, yes? How would you do it? The old negative b over 2a. Okay, but we're going to take a calculus approach to this. All right. We satisfied 2 of the 3 conditions. Mav told us it's continuous and differentiable. You all agree, yes? What we need to know then is what is f of 1 and what is f of 2? I need to see if we're on level ground. Okay, so what's f of 1 and f of 2? They're both 0. It won't always be 0. Okay, it could be something like -7 or 8, whatever. As long as they're the same value. We've satisfied all three parts of the hypothesis, so therefore we can apply Rolle's theorem. And Rolle's theorem is what we've already done. Take the derivative. F prime of x is equal to 2x minus 3 and set it equal to 0. X is equal to 3/2. Okay, what does that mean? That means that the hilltop or the bottom of the valley, but we already know it's a valley, the bottom of the valley happens when x equals 3/2. Any problems? Easy, yes? Okay. Now, is it always going to be a nice pretty parabola? Absolutely not. It's going to be different. Could you find multiple c values? Yes. One thing I would warn you is make sure, and I was about to ask that question anyways, is that c value in the interval? Is this valley or hill in the range of the spots that we're talking about? And in this case, obviously it is. 1.5 is between 1 and 2, and we're good to go. We'll see some examples where they don't fit in between the two intervals. Questions? Okay. If this is okay, then this will be really easy after I show you a picture. Okay? Shut up. Hold, please. Okay. Okay, so there's Rolle's theorem, yes? Level ground, one hill, I kept it easy, one hill, tangent line. You already told me that the pink tangent line is parallel to the gray ground. They both have a slope of 0, everything's good to go, yes? Okay, the only thing the mean value theorem does is this. Just spins it. Now my A's and B's and C's are all wiggity wiggity whack, but that's okay. Could you find the slope of that gray line?
Yeah, you could.
How?
The
Changing x or changing y.
Is that what you're going to say?
Changing y over changing
Yeah, y2 minus y1 over x2 minus x1. In fancy calculus terms, that would be f of b minus f of a, whoops, over b minus a. Again, that's y2 minus y1. For terminology purposes, that gray line is commonly called a secant line. It's a line that hits a graph in more than one spot. How would I find the slope of the pink line?
It's equal to the gray line?
It's equal to the gray line. So if I can find the gray line, I can find the pink line, right? Okay. How else could I find the slope of the pink line? Nice. Good. Okay. The slope of this line is f prime at c. And what we've already noticed, these lines are parallel, so therefore these two puppies have to be equal. Okay, so before I go to the slideshow, does that make sense? Again, all I did is stick Rolle's theorem and I spun it. Now, does it have to be angled like that? No, it could be upside down, it could be vertical, it could be all kinds of different things, but it allows us to take Rolle's theorem and not require everything to be level. We can just spin it. That's the mean value theorem. Okay, so what does the math look like? It looks like this. Okay. We still have some hypotheses that need to be followed. It has to be continuous and differentiable. We no longer have to start and stop at the same level, because, again, we saw in that picture that they weren't. And then, if those two things are met, then the next, either one of those you want to use will work. I prefer, personally, this one, and you'll see why on the next slide. On the left of that equation is the slope of the tangent line at the top of the hill or the bottom of the valley that's been spun. On the right side of that equation, we have the slope by calculating y2 minus y1 over x2 minus x1, the stuff you did back in Algebra 1. Okay, so the way I like to approach the mean value theorem is, those are those two equations again, but I like the top one because I use the buzz phrase all the time. The slope from calculus has to equal the slope from algebra. The slope from algebra is at y2 minus y1 over x2 minus x1. The slope from calculus is the derivative. However, this one people love to use. I don't know why, but I assume you see how that came about, right? Just okay. I like the top one better. Any problems? Excellent. Then let's see what this looks like in motion. Oh, well, there's a picture. I forgot about the picture. Great. We saw that already. Fantastic. Moving on. Okay. Find the MVT values. Those are the same things as the C terms. In Rolle's theorem, those C terms were our peaks and valleys. In mean value theorem, they're not necessarily peaks and valleys. They're those points of tangency that guarantee that the lines are parallel. Just like Rolle's theorem, I need to know, I think I did it. I need to know f of 2 and f of 3. Oh yeah, I forgot this. Is that function continuous? It's polynomial. Is it differentiable?
Yes.
Yeah, we're good to go. Fine. Boom. Okay, algebra. I found f of 2 and f of 7. Plugging and chugging. So I know the endpoints. I took the derivative. That's easy. Chose an easy one to start. I then calculated the slope of the secant line. In the picture it was the gray line to get 15. And based on what we talked about, we know the gray line has to be parallel to the pink line. So therefore, those two things, the slope from algebra, has to be equal to the slope from calculus. Solve. Easy peasy. 4.5. And as I mentioned on the last slide, the last question you want to ask yourself is that answer, or are my answers in the interval? Yes, 4.5 is between 2 and 7. We're good to go. That x value that I solved for is also what they call the MVT value. It's also what they call the C terms. So if you want to get all fancies in your pantsies, you could throw a C in front of this. Only one in this case. But again, you do that because it's a parabola. But also notice that this parabola, it's not the vertex anymore. It's some chunk of the parabola between 2 and 7. Questions? Make sense? Slope from algebra equals slope from calculus. Good. Now you do one. It's we're looking at two theorems, Rolle's theorem and MVT, and how they relate. So we started with Rolle's theorem and the transition to MVT. Yeah, but starting at level ground. So we took the level ground and spun it. So they're very similar, just a little subtle differences. Okay, hold on a second before you continue. Did you look at the hypothesis? Is that function continuous? No. So now what? Okay, let's back up. How do I know that function is not continuous? For our purposes, there's only two things you care about. Zero denominators and negative square roots. If you don't have any square roots, is there a zero denominator? Yes, that's 4 divided by x. Where is that function discontinuous?
X equals 0.
X equals 0. Do we care about that?
No.
Why?
It's not in the interval.
Bingo, it's not in the interval. Fine. Are we going to even attempt to offer an explanation?
Yeah, I just overslept.
I'm sorry?
I overslept. Like during my study hall.
Okay. That's great. It's discontinuous at 0. 0's not in the interval. So therefore, we don't care about it. Is it continuous from 1 to 4?
Yes.
Yeah, there's no problems between 1 and 4, so we move forward. It doesn't have to be continuous everywhere, it just has to be continuous on the interval. Get started. Go.
Negative 4 over x squared. Wait, is it negative or positive? Positive.
Or it's positive, because you have negative 4x to the negative 2.
Okay, that's 3 over 3. So then what is x? Wait, oh no. No, I gotta find the interval. So then
I understand. Yeah, so you're taking the derivative. Write that as negative 4x to the negative 1 and then
Say no.
So?
Interesting. Oh, wait.
So I had that too, and then I was like, wait, it's a correct.
That's not
the intervals between, so okay. So like that. I get to here, but then this is
Oh.
Okay, is this your algebra stuff?
yeah.
Alrighty. So,
No.
first things first. Slope from calculus equals slope from algebra. Plug in plug in 4 into the function, plug 1 into the function. When you, oh, by the way, that's a picture of the graph. Notice this continues.
Well, no, you gotta find the.
Okay,
Oh.
so calculate the slope first, and I got 1, as did many people.
Oh,
Take the derivative, 4 over x squared. Remember, negative, well, the 5 goes away, negative 4x to the negative 1, bring it down, reduce it, yeah, blah, blah, blah. Set them equal, and solve. X is plus or minus 2. What is wrong with that answer?
No.
Sarge? Negative 2 is not in the interval, so we toss it out. Only one solution, and that's when x equals 2.
Wait, I plug these in.
I think what's better. I wrote negative 4. I wrote 5 minus 4 times x to the negative 1. Bring the negative 1 down times the negative 4 to get positive 4. Reduce the power by 1, which is x to the negative 2. Which is the same thing as x over x squared. Okay? Any other questions? Great question. Natalie just asked, what did we just solve for? We solved for that point right there. Sorry, you can't see where I'm pointing. We solved for this point C.
So I need to find the slope between these two. And then plug
In
it
Rolle's
into the
theorem, that would
derivative.
be the top of the hill. In mean value theorem, it's the point where the tangent line is parallel to the secant line. So when we calculated, referring back to this picture, when we calculated the slope of 1, what we actually found is the slope of this gray line. And then when we calculated the derivative, 4 over x squared, we found the slope of that puppy. Then set them equal, because like we talked about, they have to be parallel. And if they're parallel, their slopes are equal. Set them equal and solve. What you get for x value then is that c term of where that parallel line hits the curve. And again, we looked at examples in the slideshow. I probably should have included one where no, that one had multiple answers. Never mind, scratch that. It had multiple answers, but one of them wasn't in the interval, so we tossed it out. Okay? Questions? We're good? Make sense? That is a bridge in Taiwan where they thought it would be a good idea to put the mean value theorem on the bridge. I'm going there to see it. I just have to convince my wife. I'm hoping that's a hotel to the left. I'm just going to get a room and just stare at the bridge for a week. Order in. DoorDash.
What's the symbol on the door?
What's what?
The symbol.
This symbol is a way to express the function or the location of the point.
Does that mean?